This week we're going to cover section 3.2 from Unit 3. For this section, we're talking about division of polynomials. So synthetic division, and we're going to cover a little bit of long division and how we get to the process of synthetic division. So why are we looking at division of polynomials? Well, we often use these for simplifying rational expressions or factoring polynomials in terms of polynomial division, or trying to determine if we have a factor of a polynomial. So it's a different pathway to factoring. It's also a pathway to helping us find zeros of functions, which we'll see more about in section 3.3. So we're going to start with looking at long division as a refresher, and then we're going to look at synthetic division, which is the faster and simpler version of long division. Our focus in our course is going to be on synthetic division. So if we have an expression that is dividing the function g of x by d of x, we can say that that is represented by the simplified version f of x, and f of x is equal to g of x over d of x. The resulting expression given by actually performing the division is given as f of x is equal to d of x times q of x plus r of x. Why do we have f equals d times q plus r? This is something called quotient remainder theorem, and what we're looking at here is a different way to write f of x. And f of x can be written as our divisor d times some quotient that we were able to find plus the remainder. So this is when we do things like saying 14 is equal to 3 times 4 plus 2. Or 17 is equal to 3 times 5 plus 2. So you have a divisor, and in both of those cases was 3. You have a quotient, which is the number it's multiplied, the other factor, plus what's left over, or the remainder. We have them as functions because our divisors are binomials of the form x plus or minus a constant. So our quotient is also going to be a polynomial, and our remainder is going to have polynomials involved in it in some way, and we're also going to learn a slightly different way to write it. A few key concepts here that we need to remember is if a polynomial division results in a remainder of 0, then the divisor is in fact a factor of the given polynomial g of x. That means d divides g of x with no remainder. It's a factor of g of x. If our polynomial division results in a remainder other than 0, our divisor is not a factor of the given polynomial g of x. We're going to begin with a reminder on how polynomial long division works. So we're going to use long division to determine if x plus 2 is a factor of 5x cubed minus 6x squared plus minus 28x plus 8. So let's just say x plus 2, how does it divide 5x cubed minus 6x squared minus 28x and plus 8? Just like with whole number division, long division, we have to figure out what x plus 2 can be multiplied by to give us 5x cubed. So we're looking at our first terms of each expression. So the easiest way is to say what is 5x cubed divided by x? And that would be 5x squared. We write the 5x squared at the top, and we figure out what it is when we actually multiply it out, which would be 5x squared times x plus 2, which would give us 5x cubed plus 10x squared. And so now we have to subtract 5x cubed plus 10x squared. So minus 5x cubed plus 10x squared in parentheses. And why does that matter? Because when we have to now look at it moving forward and doing the actual subtraction, we have to think this is actually, if we take away our parentheses, a minus of 5x cubed, but minus times a plus gives us a minus, so it would be minus 10x squared. So we have to switch our signs. And then we get 5x cubed minus 5x cubed is 0. Negative 6x squared minus 10x squared is going to give us negative 16x squared. And then we'll drop down the negative 28x. And now we have to do the same thing for the next term. We have negative 16x squared, and the first term of our divisor is x, so we would have to multiply it by a negative 16x. So we write our negative 16x at the top, and we figure out what negative 16x times the entire divisor looks like, which is going to be negative 16x squared minus 32x. And now we want to subtract negative 16x squared minus 32x. And again, since we're subtracting and it's a polynomial, we have to distribute this negative. So when we get rid of our parentheses, we have a negative times a negative makes it a positive, and a negative times a negative makes it a positive. So when we add them up, negative 16x squared plus 16x squared gives us 0, which is exactly what we were looking for. And then negative 28x plus 32 is going to give us plus 4x. And then we drop down the plus 8. And we see where we end up here in the very, very end. And that is, now we are going to have to do 4x over x, which is just 4. So we have plus 4. So we end up with 4 times x plus 2, and now we get 4x plus 8. So when we subtract off 4x plus 8, we had a 4x plus 8, and we subtracted a 4x plus 8. We have a remainder of 0. What that means is x plus 2 is a factor of 5x cubed minus 6x squared minus 28x plus 8. So we can write 5x cubed minus 6x squared minus 28x plus 8, and we would say that is the same as x plus 2 times, well, what did we get? 5x squared minus 16x plus 4. And so we now have our division done, and we showed that it was a factor. We're going to do one more. The next one's going to have a remainder, and then we're going to look at these and figure out how to do them with synthetic division. So let's try another one. This one has a couple of different things in it that we want to look at. One of them is that we have a missing term. Notice we have an x cubed term and we have an x term, but we do not have an x squared term. So we have to handle that first. And that's pretty straightforward. We'll do that. And then the second is we are going to have a remainder here. So we have to talk about the different ways we can write this remainder. Okay. So let's first set up our problem. We want to use long division to determine if x minus 3 goes into 3x cubed. We have no x squared, so we're literally going to write plus 0 x squares minus 2x and plus 5. So pause here and try it on your own to see if you can get the answer, then come back and unpause it, and let's see if we get the same thing. Okay, hopefully you took that break, and let's see what we've got. So this time we've got 3x cubed and x. So our first term will do 3x cubed over x. And when we do that, we come up with 3x squared. So we're going to have a 3x squared as our first term. And 3x squared times our x minus 3 is going to give us 3x cubed minus 9x squared. So we want to subtract the whole thing. So let's subtract the 3x cubed and add the 9x squared. See what I did there? I went ahead and multiplied it by the negative. So we can write it in an easier way and make it addition instead of subtraction. So when we do that, we end up with, let's see here, we end up with 3x squared, or sorry, 3x cubed minus 3x cubed is 0, which is what we were looking for. 0x squared plus 9x squared gives us 9x squared. And then we need to drop down the negative 2x. And now let's figure out what the next term would be. So we would have 9x squared divided by our x, which is going to give us 9x. So plus a 9x. And 9x times x minus 3 gives us 9x squared minus 27x. And when we subtract that, we'll flip all of our signs so we get minus 9x squared and plus 27x. And when we add this one up, we find out that we end up with 0x squareds plus 25x's. Okay, interesting. Let's see what happens. We're going to drop down the plus 5. And let's see where we go from here. So our last term, then, we would say take the 25x divided by our x, and we're left with 25. 25 times our x minus 3 gives us 25x minus 75. When we subtract it, it will be a minus 25x and plus 75. So we have no more x's, but we have 80 left over. So this is where we start coming into having a problem with remainders. So how will we even write our result for this problem? Well, we would say that 3x cubed plus 0x squared, which we don't really need to write, minus 2x plus 5 is equal to x minus 3 times, and what did we have left? Well, we had a couple of interesting things happen up here. Well, first of all, I forgot the 25. There we go. And we have a remainder. So let's see what we would write it as. We would say this is 3x squared plus 9x plus 25, but we also have that little leftover 80. So we would say plus it's 80 out of x minus 3. That's our remainder. So if you remember when we did things like how many times does 3 go into 17, we said that was 17 divided by 3. The biggest you're going to get is 5, right? 3 times 5 is 15. So we'd say it would be 5. And then when we subtract, we have 2 left over. And that is our remainder. So we would say that 17 divided by 3 was equal to 5 plus 2 over 3. So 5 2/3. It's the same idea here. We put our remainder over our divisor. Because we understand how distributing polynomials works, I want to show you a really cool trick of how we can write this in an easier to see way. We can take this x minus 3 and multiply it by just this last one as well. So if we separate it out a little bit, we can say then that we have x minus 3 times, and let's leave our 3x squared plus 9x plus 25 alone. But let's also say it's the same as plus our x minus 3 times our 80 over x minus 3. And something really, really cool happens now, because now we can cancel out these x minus 3's and essentially just be left with our remainder. And this is where that form that I showed you before that said f of x equals d of x times q of x plus r of x comes in handy, because here now we can rewrite this one last time as x minus 3 times our 3x squared plus our 9x plus our 25 plus 80, because 80 was our remainder. So it looks pretty cool that way, and it looks like it's easier to understand. So in the future, we could just write it in this way and write our divisor times our quotient. And what is our quotient? Our quotient is all of this right up here. It's everything that's highlighted in blue. Notice it's all right here. That is our Q of x. So this is Q of x. The purple is our D of x, or divisor, and the 80 is our R of x. So we have D times Q plus R, which is exactly what we wanted. While this method is effective and it's thorough, there has to be a quicker way to get to the same answer. And I will tell you, there really is, and that's what we're going to look at. We're going to look at synthetic division, so we don't have to be so bogged down in all of these steps and making sure we haven't lost anything. We have lots of steps to go through. We have lots of negatives flowing around and everything. So let's see if we can understand a faster approach that's very, very linked with what we have just done. So let's examine how example 2 would work without the variables being listed. So this is our motivation for how synthetic division is going to work. So if instead of taking this problem we just did, which I have written out, what if we removed all of the variables and we came up with a different way to look at it? Well, that would be 1x minus 3, which is going to look a little funny. And then we would have 3, 0, negative 2, and 5 here, with on the top a 3, a 9, and a 25. And let's do the same underneath. So here we had a 3 and a 9. And those are coming directly from here, right? 3 and negative 9 from there. And then we had 9 and negative 2, because that carried down. And underneath that we had 9 and negative 27. And again, those came from here. Right? And when we found that difference, we ended up with 25, and we brought down the 5. So this is the negative 2, this is the 5. And then when we did that multiplication, we got 25 and negative 75, which resulted in our 80. So we had a 1 and a negative 3 on the outside as our divisor. We had under our root, our g of x had a 3, a 0, a negative 2, and a 5 as the coefficients. Our divisor had 3, 9, and 25, and then there's all of our work. But if we look at each of these highlighted numbers, they're repetitions of the numbers directly above them. So for convenience sake, we can omit those. So we'll say that we would essentially just cross these ones out because we no longer need them. Because we knew that's what we were doing. So those ones can disappear. And the next thing that we can notice here is that, oops, let me highlight the right one. This negative 2 and this 5 are repetitions of the numbers directly above them. So we're going to omit those as well. Can you see how this is speeding up a lot faster now? So now our division looks more like a 1 and a negative 3 on the outside. Underneath, we still have our 3, our 0, our negative 2, and our 5. On the top, we still have our 3, 9, and 25. But let's see what we're left with underneath. We're left with this negative 9 and this 9. And then we're only left with this negative 27 and this 25. And then from there, we're left with just our negative 75 and our 80. So we can, in this case now, just condense this into 3 lines. And that is how our synthetic division works. Because now if we want to condense this into 3 lines, we would say that I have, and we can omit the 1 on the outside. Because the first digit of the divisor is always 1, so we can say, let's maybe forget this guy here. And so we'll cross that one out as well, just to make things even easier. So now, I'll even switch colors. Let's see what we've got. We've got it down to a negative 3 on the outside. Underneath, we still have 3, 0, negative 2, and 5. And now underneath them, we have negative 9. We have the 9 here. We have our negative 27 and our 25. And then we have our negative 75 and our 80 here. And the only thing that we don't see just yet is this 3, which we will just drop down. And on the top, we still have 3, 9, and 25. And so there's one last step that we can go through to make this a little bit easier, and that's to multiply everything by a negative so that we don't have to subtract. We can always add, because 0 minus a negative 9 is a lot to think about in your head if we're trying to do a faster way. So what we're going to say is now multiply, right? Multiply by negative 1 the divisor and each of your work steps, because now we have equalized out this negative in 2 places. So it works out great because we haven't really changed what the problem is asking, but we have now found a way to just add instead of subtract every time. So when we do that multiplication, what happens is we reduce this down to, let me find another color here to write with. Now instead of negative 3, we're going to have positive 3 on the outside. Underneath, we still have 3, 0, negative 2, and 5. And you can guess that the top is still going to be 3, 9, and 25. That hasn't changed. But what has happened is underneath, we're still just going to drop down this 3. But now we're going to have a positive 9, and 0 plus 9 is 9. Much easier than 0 minus a negative 9. And then we have a 27 that's positive now, and negative 2 plus 27 is 25. Much easier than negative 2 minus a negative 27. And then the last one would have been 5 minus a negative 75. And in this case, instead, we have a positive 75 to get us to our 80. This is how synthetic division works. This is how it's tied directly to the long division that we just did. So, is there a process? And the answer is yes. I have written out the steps for how to do this all together. And the last step really is now, how do I write my solution? How do I write what I found? I now have this 3, 9, 25, 80 at the bottom, and I don't even know what it means. Well, what happens is you'll notice when we did long division, all of our quotients ended up with a degree, polynomial of degree 1 lower than the one we started with. So all of the degrees are 1 lower than what g of x had. So in this case, we now have 3, and this instead of being x cubed is now x squared. And instead of being x squared, 9 is now x. And instead of 25 being an x, now it's going to be a constant. And this is our remainder. So we end up with 3x squared plus 9x plus 25 plus 80 over x minus 3, which is exactly what we got when we did this with long division. And again, if you wanted to write it as in the remainder theorem formula, we could make this x minus 3 times 3x squared plus 9x plus 25, and then plus our 80. It works out the same way. So let's see this process. So I wrote it out just like we did it on the last page, but now we're going to practice it a lot. So to perform synthetic division on a function f of x that is given as g of x divided by d of x, remember d is our divisor, let's summarize this by saying, number one, write g of x in descending order of powers of x, if it isn't already, and then enter the coefficients under our division symbol. Enter a 0 for any missing terms, even if it's the plus 1 at the end or any kind of constant at the end, that still could have a 0 out there. Okay. Step 2, enter the value of k to the left of the division symbol because we are dividing by x minus k. So what that means is if you're dividing by, so if d of x equals x plus 4, then k is equal to negative 4. If we're dividing by x minus 4, then k is just 4. So remember, we want x minus k. So however you need to change k to make it in the form of x minus, and then that's k, whatever's left. So if it's a plus, we switch the sign. And then we want to bring down our first term to row 3, and then multiply that term by k, place it on row 2, add them up to find the next value in row 3. Multiply that by k, put it in row 2, add them up, enter it in row 3, and repeat this until you run out of coefficients in row 1. Once you've done that, if you have anything left over, that's our remainder. And then we want to write f of x using the coefficients in row 3 and a polynomial whose degree is 1 fewer than that of g of x. And in that way, we're going to find f of x equals d of x times q of x plus r of x. It sounds a little complicated. Once we get the hang of it, it goes very, very quickly, and you hopefully will really like synthetic division. So let's try it. Let's look at x minus 2 being a factor of 6x cubed minus 19x squared plus 16x and minus 4. Let's see what it's going to look like here. So what I'd like for you to do is follow along with this one, and then on the next one, I'd like for you to try it on your own. So in this case, we have x minus 2 is our x minus k. That's our d of k, or d of x. That tells us that k equals 2. So we have a divisor on the outside of 2, and underneath, we take our factors 6, our coefficients of our polynomial 6, negative 19, 16, and negative 4. Notice we don't have any zeros this time. We have x cubes, there's 6 of those, x squareds, there's minus 19 of those. X's, we have 16 of those, and coefficients, we just have, or sorry, constant, we just have a minus 4. So this is row 1. Now, let's start doing the process of synthetic division. First step, drop down this 6 to row 3, because this is row 2. And this one is row 3. So we drop down the 6. The next step is to say I have 6 times 2, and that goes here. And that's our 12. Then I do negative 19 plus 12 gives me negative 7. And then I take negative 7 times 2, because that's our k, is negative 14. 16 minus 14 is 2, and 2 times 2 gives me 4. Negative 4 plus 4 is 0. I'm going to do it one more time. Okay, so we have k equals 2 because it is x minus 2. So 2 is going into, and we have 6x cubes. We have negative 19x squareds. We have positive 16x's and minus 4 as our constant. From here, we draw our line down here. This is all row 1. We drop the 6. And we say 6 times 2 gives me 12. Right? 6 times 2 gives me 12. Negative 19 plus 12 is going to give me negative 7. And then I take negative 7 times the 2, which is k, and I end up with a negative 14. 16 plus a negative 14 is like 16 minus 14, so it is 2. And then I do 2 here times our k, which is 2, which gives me 4, and negative 4 plus 4 is 0. So no matter which one you followed along with, we could say then that 6x cubed minus 19x squared plus 16x minus 4, if we try dividing it by x minus 2, we're going to get 6. And remember, we dropped the degree. It was a cube, now it's a square. Minus 7 was an x squared, now is an x. And then plus 2 was an x, now is a constant. So this is the same. If we multiply both sides by x minus 2, we can put it in that d, or f equals dq plus r, by saying f, which is 6x cubed minus 19x squared plus 16x minus 4, is the same as 6x squared. Oh, here, let's do it in the same order. So we have our divisor first. So it'll be x minus 2 times our quotient, which is 6x squared minus 7x plus 2, plus our remainder, which is 0, so we don't need to write anything. And this is our answer. So we can either write it this way, or we can write it this way. So when you're working on the online homework, make sure you're being very clear about which form the homework is asking you to write the solution in. I want you to try this one on your own. This one asks if x plus 2 is a factor of 3x cubed plus 8x squared plus 5x plus 7. So what you want to do is you want to find 3x cubed plus 8x squared plus 5x plus 7 divided by x plus 2. And remember, if it's a factor, we shouldn't have a remainder. So let's see if it is. Or if it's not, let's write it in dq plus r format. So I want you to pause it and see if you can set up the synthetic division first. So pause for a few seconds, write out your synthetic division, and come back. Okay, hopefully you have tried this so we know that our divisor is x plus 2, which is the same as x minus negative 2, and this is my k. K is negative 2 this time. So we have negative 2 on the outside, and underneath, let's grab our coefficients, which were 3x cubes. We have x squared, that's 8. We have x's, which is 5, and we have constants, which are 7. No zeros for us this time. Now I want you to pause one more time and try to complete the synthetic division. Hopefully you took a moment to do that and didn't just let it play. Our first step is to drop the 3 down, then 3 times negative 2, right? 3 times k, and k is negative 2 this time, gives us a negative 6. 8 minus 6 is 2. 2 times negative 2 gives us negative 4. 5 minus 4 is 1, and 1 times negative 2 is negative 2. So this time we have a remainder. So we have our x squareds, our x's, our constants, and our remainder. So if we wanted to write out our solution here, we could say in this case that 3x cubed plus 8x squared plus 5x plus 7 can be written as our divisor, which is x plus 2, times our quotient, which is what we have left, right, which is what we have left here. This is our quotient. So that's our 3, 2, and 1. So 3x squareds plus 2x's plus 1. And we would say plus our remainder, which is 5. So that would be our solution. And again, if we wanted to, we could have just said that the division itself was 3x cubed plus 8x squared plus 5x plus 7 divided by x plus 2, we could say is just this 3x squared plus 2x plus 1, and then plus 5 over x plus 2. So there's a couple different ways we can write this solution. We're going to do another one, of course. So let's try this one and see if we can go a little quicker this time. So now we have x plus 2, so k is negative 2. So we have negative 2, and inside we've got a negative 1. Oh, but notice we have no x cubes. So we have to have a 0 for the x cubes, a 3 for the x squareds, a negative 4 for the x's, and a negative 5 for the constants. And now we want to drop our line here, drop down that first coefficient to be a negative 1. And now negative 1 times negative 2 is 2. 0 plus 2 is 2. 2 times negative 2 is negative 4. 3 plus negative 4 gives us negative 1. Negative 1 times negative 2 gives us 2. Negative 4 plus 2 gives us negative 2. Negative 2 times negative 2 gives us 4. So we get a negative 5 plus 4, which is a negative 1. So a little bit different now, but still similar. This is still our q of x. This is still our r of x. So if we wanted to write out our factorization here, we would say that negative x to the fourth plus 3x squared minus 4x minus 5 can be written as, remember we drop our degree by 1, it would be our x plus 2 times, and these guys end up being negative x cubed plus 2x squared minus x minus 2, and our remainder is minus 1. And again, one more time, we could have also written it, and that's our answer, or we could have written it as negative x to the fourth plus 3x squared minus 4x minus 5 all over x plus 2 is the same as our negative x cubed plus 2x squared minus x minus 2 minus 1 over x plus 2. They're saying the same things. We have one more theorem in this section. So if we see, as we have seen, when division of g of x by x minus k yields a remainder of 0, the divisor is a factor of g of x. So x minus k is a factor of g of x. However, the same is not true when the remainder is anything other than 0. So we have a theorem that essentially says the same thing in two different ways. So the first part says a polynomial g of x has a factor x minus k if and only if g of k equals 0. And this is why we would call it a zero of function g of k. This is what we're going to be learning in section 3.3. Also, I apologize for the typos on there. I will fix the one that's uploaded to Blackboard for you. Number 2 says if a polynomial g of x is divided by x minus k, the remainder is g of k. When g of k is 0, x minus k is a factor. When g of k is not equal to 0, x minus k is not a factor. So that one sounds a little different, but we can actually put this to use pretty easily. Let's see it on the next couple of examples. So this first one says, use the remainder theorem to determine if x plus 2 is a factor of 4x cubed plus 24x squared plus 48x plus 32 and confirm it with synthetic division. So we're going to look at this one and see what happens. So what is k? Well, we have our d of x this time is x plus 2. And remember, it has to be x minus k. So that tells us x minus a negative 2. And this tells us that k equals negative 2. And this is our function that we were looking at, g of x. So let's find g of k. Let's find g of k, which in this case is g of negative 2. Okay, let's do it then. G of negative 2 equals 4 times negative 2 cubed plus 24 times negative 2 squared plus 48 times negative 2 plus 32. If you plug all of this into your fancy calculator to see what you get, you end up with 4 times negative 8 plus 24 times 4 minus 96 and plus 32. So let's see what happens when we find out these numbers. We end up with 4 times negative 8 is negative 32. 24 times 4 is going to give us also 96. And then we've got minus 96 and plus 32. So funny thing happened there. Everything canceled out. So g of negative 2 is 0. So we would say here then, our remainder theorem says that x plus 2 is a factor of 4x cubed plus 24x squared plus 48x plus 32. Now let's confirm this with our synthetic division. Well, our synthetic division says we have negative 2 on the outside. Underneath, we have, let's see here, 4x cubes, 24x squareds, 48x's, and 32 constants. Drop our line, drop down the 4. 4 times negative 2 is negative 8. 24 minus 8 is going to give us 16. 16 times negative 2 gives us negative 32. 48 minus 32 is 16, and 16 times negative 2 is negative 32, and our remainder is indeed 0. Funny how that works. So we here now found out that we could write 4x cubed plus 24x squared plus 48x plus 32 as x plus 2 times, and here's our divisor, 4x, drop it down by 1, not a cube anymore, but now a square, plus 16x and plus 16. Yes, we could actually go ahead and factor out a 4, see if there's anything else that we could factor. We'll get to some more of that a little bit in a minute here. But we could find this factorization right here. And yes, we could pull a 4 out of that one and make it a 4, and then that x plus 2, and we would have x squared plus 4x plus 4, which is the same as x plus 2 and x plus 2. So in the end, we actually have 4 times the quantity x plus 2 cubed. But we could, this is our final factorization if we wanted to factor it completely. So again, just make sure you're reading the directions on the homework to see if it needs to be factored completely, because sometimes once we find one factor, we can keep going. And this is something that's going to be really useful when we start looking at zeros of polynomials and then use them for graphing when we get into section 3.3. We have one more problem like this to try. So let's use our remainder theorem to determine if x minus 1 is a factor of 2x to the fourth plus 3x squared minus 5x and plus 7, and we're going to confirm it with synthetic division. In this case, we could also do the synthetic division first and then find f of our k and see if they're the same. They should be. If we did everything right, they should be. So it's also a nice way to check your work. So pause here and try this one and see what you get. Well, hopefully you found, since our divisor is x minus 1, then hopefully that means you realize that k equals 1. So find g of 1, and that would be 2 times 1 to the fourth plus 3 times 1 squared minus 5 times 1 and plus 7. So really we get 2 plus 3 minus 5 and plus 7. The 2 plus 3 is 5, and 5 minus 5 is 0. So we're left with a remainder of 7. And since we have a remainder that is not 0, x minus 1 is not a factor of 2x to the fourth plus 3x squared minus 5x plus 7. So we can say that for sure. It is not a factor. But let's see what happens when we do our synthetic division. When we do that, we have k is 1, so we have 1 on the outside. And underneath, we have our 2. Notice we don't have any x cubes, so we need a 0 there. We have 3 for the x squareds, a negative 5 for the x's, and 7 for the constants. We draw our line, drop down our 2. 2 times 1 is 2. 0 plus 2 is 2. 2 times 1 is 2. 3 plus 2 is 5. 5 times 1 is 5. Negative 5 plus 5 is 0. Oh, that looks good, except it's not the last entry, so it's not a remainder. Now we have 0 times 1 is 0, and 7 plus 0 is 7. Here is our quotient. Here is our remainder. So what ends up happening here is we have 2x to the fourth plus 3x squared minus 5x plus 7 is now equal to x minus 1, our divisor, times our quotient, which is 2x. Drop the degree by 1. It was 2x to the fourth. Now this is 2x cubed plus 2x squared plus 5x, and no constants. So we have nothing else to add to that. And then we do have a remainder of 7. So this is how we would write this one in f equals dq plus r notation. Or if we wanted to write it out the long way, we also could have said that 2x to the fourth plus 3x squared minus 5x plus 7 divided by x minus 1 is our quotient, 2x cubed plus 2x squared plus 5x plus our remainder over our divisor. So now that we've finished synthetic division, make sure you're working on the online homework for section 3.2. I have moved that homework out to being due the night after our exam. So you have until Wednesday night to complete online homework 3.2, and I'm going to give you a written homework on Tuesday when you turn in your exam. I'm going to give you a written homework to turn in with this for Thursday.